In our introductory pump video, we talked a little bit about the ideal volumetric flow rate and pressure-torque relationships of a pump. But now let's start exploring some of the inefficiencies of a hydraulic pump, and really we're looking at the energy loss terms of a hydraulic pump. So in a pump, there's lots of different sources of energy loss. I'm going to pick a certain hydraulic pump architecture, which happens to be an axial piston pump, but realize that what we're talking about here is broadly applicable to the other styles of positive displacement pumps that we talked about in the previous lecture. So I've got a picture of an axial piston pump, and if you recall how it works, I've got a swash plate that's at an angle here. It is not moving, and then I'm rotating this block with all the pistons relative to that. So this is driven by the shaft of the pump, and then as this rotates, these pistons reciprocate back and forth, causing the pumping action. So they move nearly sinusoidally in their pistons, or in their cylinders. So let's talk about a few sources of the energy loss. The first one that I'm going to focus on here is in the piston cylinder itself. And so in that joint we have one, leakage of the high pressure flow past the small clearance that we have between the two of them. So this is purely a clearance. We don't have any other types of seals in this area. The second is we have viscous friction between these two, between the piston and the cylinder, so these moving parts. Other sources of energy loss in this pump, we have bearings, and they have friction. Not only do our rolling element bearings that are supporting the shaft have friction, but also we have a number of hydrostatic bearings in our system, where if you can imagine these pistons right here, the slippers of the pistons, are in contact with that angled swash plate. Well, they have a high pressure flow path coming from the cylinder to the slipper joint, and then that becomes a hydrostatic bearing, creating clearance between the two of them. Well, there is viscous friction associated with that bearing. We have seal friction. We need to be able to seal the case of the pump from the outside, and so we have friction associated with that seal. We have fluid compressibility, because normally we think about oil as being incompressible, but there is a small amount of compressibility, and that adds up to energy loss, because every time the low pressure fluid comes in here, we first of all have to compress it, maybe 3% with most hydraulic fluids, and then we push most of the fluid out of the cylinder, but there's a small dead volume left, and that dead volume of fluid is then open to tank pressure, and we decompress it, therefore losing that energy that went into compressing the fluid. And then we have valves that connect these cylinders to high and low pressure ports. And these valves have associated leakage with them, as well as viscous friction, and throttling loss, as well, as we are forcing flow across the partially open ports. So many sources of energy loss in a pump. What I want to do is do kind of a detailed dive into one specific form of energy loss, which is at the joint of the piston cylinder, at their interface. So what I've highlighted there, and it is this pump right here, and right between this piston and the cylinder block. That's the joint that I really want to take a closer look at. So I have a diagram of it here, just a single piston of this multi-cylinder pump, and it could be an axial piston pump like this. It could be another style of piston pump. It really doesn't matter. But what I want to focus on is this interface between these two surfaces. And at this interface, we have, first of all, the velocity of the hydraulic, or of the piston itself, which is moving to the left. So I've got a velocity here. And I know that I have a zero slip boundary condition between the fluid and the piston itself, and also between the cylinder and the fluid. And so if I draw a velocity profile, it would look something like this for a Newtonian fluid, where I've got a velocity gradient along that gap between the piston and the cylinder. Now, I've drastically exaggerated the size of this gap here, but just to give you a feeling, we're talking, somewhere in the 10 to 30 micron type of a gap region here. So fairly small, but still we get a reasonable amount of viscous loss because of that small gap, but also a large amount of leakage. So I've got this velocity gradient here, which we refer to as a Couillette flow, which is due to the moving of the piston right here. So what I've labeled right here, this would be Couillette flow. And then superimposed on that, I'm going to have the pressure-driven flow. So I'll grab a different color. And now I've got this pressure-driven flow where I've got a higher pressure in my cylinder, PC, and then on the other side of my piston, I have the case pressure, which I'll refer to as the case here, and that is then going to drive a parabolic velocity gradient, and we refer to this as a Poiseuille flow. P-O-I-S-E-U-L-E. So I'm superimposing these two flows on top of each other. And first of all, the Couillet flow, because it's going to be going in the direction that my piston's moving, I'm going to have a net zero flow rate. But the parabolic flow created by the Poiseuille flow, the pressure-driven flow, that will have a net leakage, which results in the energy loss. So let's start modeling these two terms. First of all, let me make a bunch of assumptions. First, I'm going to assume that I have a concentric piston to cylinder interface. It actually turns out that if my piston is all the way offset to one side, I increase my leakage about 150%. So this assumption does make a big difference. I'm going to assume that I have steady flow, that it's fully developed. Because this gap is so small, my Reynolds number is going to be small. Therefore, I have laminar flow, incompressible fluid, and that all the velocity is in the axial direction. Now, with this, I can then start to model the leakage, and I'm going to model it using the equation typically used for flow between parallel plates, laminar flow between parallel plates. And in this equation, we usually refer to the width of the plates. Well, in this case, I've got a piston cylinder, and I can think of that width as just wrapping around the circumference of each piston. So in this case, I'm replacing the width by the circumference, which is that pi d, the first piece of the equation there. Now you'll notice that there's a cube of the clearance here. So C is the radial clearance between the piston and cylinder. So that clearance is enormously important for how much leakage flow rate I have. And then in the denominator, I've got the length as well as the dynamic viscosity of the fluid. And obviously this is also proportional to the pressure differential. So if I want to calculate what the energy loss is, I'm going to integrate the pressure differential times the flow rate, the leakage flow rate with respect to time. And you'll notice here that I'm doing this over half of a cycle. Now the reason I'm doing it over half of a cycle is because I only have this pressure gradient for half the cycle when I am exposing the outlet here to my high pressure port, if you will. When I'm at tank pressure, that's very close to case pressure, and so I'm going to say I don't have any leakage during that period of time, only when I'm connected to high pressure, and therefore half of the cycle time. So here I'm trying to calculate the energy loss per cycle, and because I'm only experiencing pressure half the cycle, I'm going to use that time. So I can say half the cycle is just going to be pi divided by the angular velocity of my pump. And then I substitute that in, and then I can integrate this term, and as I integrate it, I get a term or an expression for the energy loss per cycle of my pump for the leakage here. And you'll notice again that it's a cube of the frequency, it's a square of the pressure differential. So as we're increasing pressure, this leakage term is going to go up with the square of the pressure, so this becomes quite important. Now let's also take a look at the friction. So our friction, well, we're going to be concerned with a force and a velocity. And so first of all, my friction force, I'm just going to use Newton's law of viscosity here, rearrange it a little bit, and I can then say the surface area this is acting upon is just the circumference of the piston multiplied by the length of it. And I'm going to neglect the fact that perhaps the length that this is acting upon might be changing as I'm moving through the stroke. So I'm going to assume that my length is constant here. And then I have this term here where I've got velocity in the numerator and the clearance in the denominator. But we're only linearly equating this to clearance, not the cube like we had with the leakage term. Now to get the frictional energy loss, I'm going to integrate this, the force and the velocity with respect to time, again over a cycle. But now because this viscous loss is occurring both during the high pressure zone and the low pressure intake stroke, I have to go across the entire cycle with my integration limits. So I need to get a feeling for what the velocity profile looks like in my piston. In an axial piston pump, the piston position is very close to a sinusoidal displacement. Therefore, I can take the derivative of that and get the velocity with respect to time. So I've got this term for velocity. I then substitute that in, and now I can equate this energy loss and this integral in a little bit more easy to manageable fashion here. Now, you might be looking at this and saying, I don't quite remember what the integral of the cosine squared term is here. Well, it turns out to be a very simple value when we're integrating it from 0 to 2 pi over omega. This term right here ends up just being pi over omega. So when we substitute or integrate that and then plug that in, we get this for the frictional energy loss per cycle. So now that I've got these two different terms dealing with the piston-cylinder interface, I can add these two up and then start to look at the trade-offs between them. And this is one of the classic engineering trade-offs where I've got so many competing variables. If you imagine that I add these two terms that are boxed here, in one of them I've got the cube of the clearance in the numerator, and the other one I have the clearance in the denominator. In one of them I've got the length in the numerator, and the other one it's in the denominator. And again, I've got multiple trade-offs dealing with pressure and quite a few number of things. I want to talk about how we evaluate a couple of these. So I'm going to take a little look at what happens as we trade off the clearance and the length of the piston. So what I'm going to do is I'm going to take the two equations that I created, and I'm just going to simply code them in MATLAB and then create a plot of what the energy loss looks like, the total energy loss for this piston-cylinder interface. Now we're going to talk a lot more about simulation tools later in this class, but I just want to give you a feeling for how I would plug these two equations in to be able to understand this relationship a little bit better. So I'm going to jump from here right into my MATLAB code, and I'll give you a little highlight of what I'm doing here in the code. And what I first of all have is, as I go down here, I'm going to define my variables. And I've picked some fairly common values here, 21 megapascals, about 3,000 psi, a diameter of a piston of a centimeter, an angular velocity of about 60 hertz, which would be 360 revolutions per minute, a very common pump speed. I've got a stroke of a centimeter for the piston, the movement back and forth, and a fairly common dynamic viscosity for a hydraulic oil. Now, I keep going down here, and now I'm also going to set up arrays here for the clearance, C, and the length of the piston, L. And so I'm setting these up between reasonable values, and you might say, how do you know what reasonable values are? Well, it really kind of comes from experience, having known what most pumps are manufactured at, and also saying, what would I reasonably want to try to manufacture? What would I want to try to tolerance these at? Now, can you imagine trying to tolerance a piston-cylinder interface to have smaller than a 5 micron radial gap? That gets really expensive to manufacture. So I've defined those. I then just need to put these into a grid, a 2D grid for the clearance and for the leakage, and then I can write my two energy loss equations. So I've literally copied what's on the PowerPoint slide in the back onto my MATLAB code here for the leakage energy loss and for the viscous friction energy loss. I then am going to add these two up, create a three-dimensional plot, and then just create some X labels, Y labels, the Z label, and then put a title on the plot. So fairly simple code. It's posted on the MOOC site, so you're welcome to take a look and play around with it yourself. So what I'm now going to do is I'm going to go ahead and run this, and it's going to create this plot that I mentioned. And so you can see that on this lower right axis, I've got the clearance in microns, and then I've got the piston length on the left axis, and on the Z-axis, I've got the energy loss. So again, this classic trade-off here, and you'll notice that where it's driving me is it's driving me towards very small clearances, and therefore very small or short lengths of the piston. Now, I was saying I really don't want to manufacture these very tight tolerances, so quite likely I'm going to say, all right, maybe 10 microns is the very smallest gap that I want to have. And then I can say, all right, let me take a cross-sectional slice of this plot at 10 microns, and then I'll find a minimum of the energy loss, which will drive me towards a desired length of my piston. So again, classic energy loss trade-offs in a pump, and just one very small example out of the many forms of energy loss in our pump. So we get a plot that looks something like that. Now, how do you do this for a pump that you might buy from a manufacturer? Now, you could try to model all these, but that means you have to disassemble it, you have to inspect everything. There's a lot of unknowns going on here. What more often happens to treat all of these energy losses is we say, I recognize I have all these losses. Now let me characterize these experimentally. So I'm going to run a large number of experiments and really develop a map of the efficiency as a function of perhaps the pressure, the speed, perhaps the volumetric displacement of the pump, and then take all of that and curve fit it. And these are some common equations that are used. So you might remember that our classic or theoretically equations was just Q is equal to omega d over 2 pi. Now X is just the fractional displacement of the pump. But what's now in the brackets here, this is the efficiency term. And so for our volumetric efficiency, we have, first of all, our slip coefficient. This is the leakage term. And then we have our second term right here, where we have the bulk modulus in the denominator. Well, this deals with the fluid compressibility. So these are the two terms that are being added together to come up with the volumetric efficiency. On the mechanical efficiency, which is dealing with the torque-pressure relationship, here we again have two different terms. The first one is a viscous energy loss term. The second one is a Coulomb friction term. So I've got those two terms. They are coming together to predict a mechanical efficiency for this pump. And then we can take that experimental data, create this model, and then use that for our simulations. And this is more often what is done instead of trying to model the nitty-gritty details of all of these different forms of energy loss in a pump. So, in summary, we've discussed some of the major forms of energy loss in a pump. We did a deep dive into one specific example, and I hope that this just forms an example that you could then use for the other forms of energy loss in the pump. And then we also talked about how we can take experimental data, fit that to curves, and then create these maps that we then use for other simulation work.